Put basically, erosion is the removal of rock or sediments from their original location, through factors such as water, wind, ice, gravity, or biotic interaction. All of these agents entrain particles and deposit them in different locations. As you can see, water eats its way through a landscape, carving gully to canyon-sized rifts in the landscape, depending on time. Strong winds are able to lift sediments and deposit them elsewhere. Large glaciers move slowly through a landscape but take with them much of the land in their wake. Gravity-forced erosion transports large sections of rock to lower elevations, and biotic interactions disrupt soil stability in some cases, and a combination of other factors can lead to erosion. The rate of erosion is dependent on a variety of factors, but none more so than climate and topography. In turn, climate is controlled by latitude, the proximity to large water bodies, wind patterns, and changes in elevation. Because of this, climates around the world vary. Climate is the main driver of temperature and precipitation. The intensity of rainfall is one of the main drivers in the rate and degree of erosion in a landscape. And because of this, during large rainfall events, more particles are able to be moved due to an increase in surface runoff over a landscape. The shape of a landscape also affects the amount of erosion. The shape of the slope, whether it be flat, concave or convex, and the angle of the slope have been found to greatly influence the amount of erosion in a landscape. Also affecting the erodibility is the material of which makes up the landscape. Soils may erode faster or slower depending on soil or sediment characteristics. Many studies have been undertaken to determine which factors have the greatest effect on erodibility of a landscape. Sensoy and Cara 2014 found that it was in fact the uniform or flat slopes which created the largest amount of erosion, while the concave slopes generated the least. Tobias et al. 2010 found that throughout the San Gabriel Mountains, the rate of erosion increases non-linearly with steepness of a slope. And Bartman et al. 2011 found that especially in semi-arid regions, rainfall events are responsible for the main part of soil erosion. This was found using event-based soil erosion models, where 4 typical rainfall events were trialled on a medium-sized catchment in southeastern Spain. Because erosion is ultimately dependent on climate and landscape form, many variables need to be tested to determine if this is indeed the case. Lab Group A decided that testing changes in rainfall intensity and a concave or convex slope type would provide information about the main driver of erosion on specific soil types. Erosion can be measured using 2 types of terminology. Firstly being the degree of sediment transport, which can be in tonnes per hectare per year, or in the average drop in elevation in millimetres per year.
Soil was extracted from the Pilbara region and placed in a desktop catchment which simulated a constant rainfall event as the sprinklers were turned on to their maximum. The soil was very fine-grained, loosely packed with occasional rock pieces. The catchment was firstly filled with river sand to about halfway up, and then the white soil was placed on top. Both concave and convex profiles were created in weeks 1 and 2 respectively. Runoff samples were taken at 15-minute intervals for 2 minutes, and the experiment ran for approximately 1 hour. The trays were firstly weighed before filling up with sediment and water. They were then placed in an oven, dried, and weighed again. The rate of erosion was then calculated using these weights and the measurements of the catchment. Toothpicks were also placed at 20-centimetre intervals within the catchment, with a black line marking the current level of the soil before rainfall began. The toothpicks were left in the soil for the duration of the experiment, and the difference between the black mark and the new soil height was measured in order to see the amount of sediment that had eroded. The second experiment was another larger rainfall apparatus that was set up to trial the rate of erosion for a rocky soil type. The rainfall simulator generated more intense rainfall resembling a storm event. The 3 catchment troughs were placed on a slight angle with a funnel chute coming out of the front of each tray. From this funnel, water and sediment was collected every 3 minutes and 15 samples were taken. Like the previous experiment, these jars were weighed beforehand and the wet and dry weights of the soil were taken. Samples were only being taken once runoff began, and the experiment was run for approximately 45 minutes, taking samples every 3 minutes for 30 seconds. From the recorded weights, the degree and load of eroded sediment was calculated. All class data was collaborated and analysed in order to observe the erosion rate for different soil types.
The rainfall intensity experiment yielded expected results with regards to the rate of erosion from the simulated bucket catchments at different rainfall intensities. In the first week, the rainfall apparatus simulated a storm event with an average rainfall intensity of 29.1 mm per hour. The average sediment yields from the 15 samples taken from each of the 3 replicate catchments under the simulated storm event are illustrated in Figure 1. The sediment yield peaked with the second sample after the onset of runoff, after which it remained at a relatively constant level. This trend was consistent for samples across all 3 replicates. Samples were taken for 30-second periods, from which the average erosion rate was calculated to be 5.49 grams per 30 seconds. Factoring in the catchment surface area of 0.56 meters squared, this gave an average erosion rate of 10,300,508 tons per kilometer squared per year. The second week had a rainfall intensity of 13.01 mm per hour, and generated far lower sediment yields, as displayed in Figure 1. The level of erosion generated throughout the simulated time period remained at a relatively constant low level. The average erosion rate was calculated to be 0.14 grams per 30 seconds, which over the bucket catchment area is equivalent to 256,230 tons per kilometre squared per year. The hill slope geomorphology experiment was largely flawed, with a lack of experimental consistency and a number of failed replicates. The uniform slope replicates did not yield any runoff, while 2 of the 3 convex replicates were unable to produce reliable results. The first replicate of the convex slope was unable to generate runoff, while the second calculated negative results as a result of weight measurement errors. The final replicate of the convex hill slope was able to produce values for the sediment yield, which are illustrated in Figure 2. However, they have no comparative results. The 3 simulated concave hill slope replicates were able to generate reasonably consistent values. Replicates 2 and 3 produced the same total erosion value of 1.6 grams from the 4 samples, while replicate 1 gave slightly lower values, consistent with the lower runoff generated from that catchment. There was no consistent increasing or decreasing trend in the sediment yield over time for the 3 concave replicates. The averages of the samples from the 3 concave replicates are also displayed in Figure 2, and can be considered more reliable. Evaluation of the runoff values showed that the differences in erosion rates between replicates and between the concave and convex results could be attributed to the level of runoff generated from the catchment, with runoff levels from the convex catchment being lower than that from the concave catchments. The convex sediment yield can also be seen to begin to trend upwards over time, which is in accordance with an increasing level of runoff generated from that catchment over time. For the simulated conditions in the desktop catchment bucket models, the average erosion rates from the concave replicates was calculated to be 214,332 tons per kilometre squared per year, while the average erosion rate from the convex catchment was calculated to be 134,512 tons per kilometre squared per year.
The previous results show that the average erosion rate for a concave profile was 0.15 grams per minute, whereas the convex profile showed a lower rate of erosion at a rate of 0.09 grams per minute. The concave profile also has higher sediment loads. This rejects the hypothesis that concave slopes generally produce the higher rates of erosion. However, there are many limitations to our data, ones which shall be discussed later. Initial observations towards the concave profile showed rain splash action. This forms the initial stages of sediment entrainment, detecting small sediments that become transported downslope by surface water flow. We also experience soil armouring, which generally tends to decrease the amount of soil loss and erosion from a catchment. This, however, is unproven in our results due to the initial problems in recording the convex profile data, meaning comparisons between the two were difficult. Some groups that conducted research could not collect any data due to lack of runoff, and the only observations shown were pooling at the surface. This therefore made the convex data inconclusive, as only one group successfully managed to collect enough data. In our rainfall intensity simulations, it was shown that in week 1, higher rainfall intensities were recorded than in week 2. It is therefore no surprise that the catchment in week 1 produced higher sediment loads than week 2. Additionally, the soil textures between the 2 weeks were changed. The catchment in week 1 was compiled of much finer sediments, whereas in week 2, the large rock content of the catchment was increased. This increase in large rocks can account for the decrease in sediment loads produced in week 2, as larger rocks require a larger amount of energy to detach and become entrained. The higher runoff rates in week 1 could also be attributed to the decrease in surface roughness in comparison to week 2. The larger rocks in week 2 can interfere and slow the movement of water downslope. It can also be said that as the rainfall intensity has been increased, there is a greater volume of water being delivered to the catchment, and therefore runoff rates are increased. We found that there were several limitations to our report. For instance, the uniform slope conducted in week 1 produced no runoff, as we believed the slope was too gentle, and therefore sediments took too long to become saturated. This meant that this catchment could no longer act as our control. In week 2, there was missing convex data. This could be due to catchment still being wet from the previous concave experiment, and therefore meant there was no sediment transportation, and some catchments generated no runoff. There was also time constraints towards this experiment. We believe that 4 weeks of labs was not enough time to complete the necessary desktop catchment simulations. For instance, the uniform and convex catchments both needed to be repeated in order to get accurate and representative data. This therefore meant that our results are not valid and could not be used towards any scientific research. There are gaps in data and inaccuracies in data where averages have been taken. From our results, we can see that in this experiment, the concave profile produced a higher sediment load than the convex profile. However, if we look at our previous limitations, the convex profile had a lot of missing data, and therefore, in order to get a representative result, this profile would need to be repeated, and therefore we may see very different results. The catchments, which have a finer sediment load, also tend to produce greater runoff rates and sediment loads in comparison to coarser sediment catchments. This could be due to the lower energy required to entrain the finer sediments. We also found that higher rainfall intensities tend to produce greater runoff rates and sediment loads. With an increase of water entering a catchment, there comes an increase in energy. This increase in energy can be used for sediment entrainment and can therefore explain the higher sediment loads as well as runoff rates. We also believe that in order to enhance our research, future research could test the change in slope, angle, testing runoff rates and erosion details in order to gain a more representative result on these type of catchments.